Good afternoon. This is Dr. Olson for Meteorology 2010 at Daytona State College. In the next series of videos, we will be discussing Chapter 2, Warming the Atmosphere, from Dr. Ahrens' textbook, Essentials of Meteorology. As you can see, we'll be doing this chapter in 3 sections, talking about energy and heat, the energy budget, and seasons. We'll divide the chapter into 4 or 5 different videos, so stay tuned for the future videos as they come up. We'll start off talking about energy and heat. Now, what is energy? Energy is pretty much the ability to do work. In other words, it's the ability to push or pull some form of matter, some object. So, for instance, you wake up in the morning, you eat a bowl of Wheaties, you have the energy to move around. You have the energy to do your homework, whatever. You have energy, the ability to do that work. Now, there are different types of energy. One type of energy that we often deal with is what we call potential energy, which is the potential for work. Another term for this would be stored energy. For instance, you eat up your Wheaties in the example I just gave. That energy is now stored inside of you. It's ready to be used. That is potential energy. When it comes to the atmosphere, though, we're more concerned with kinetic energy, which is the energy of a moving object. So you've eaten your Wheaties, you have that potential energy. Now you start using it to move, say, a file cabinet or something. You have transferred energy from potential to motion or kinetic energy. Now, how do we measure kinetic energy? By something we call temperature. The higher the temperature, that's an indication of higher kinetic energy in that object. So hot soup has a high amount, the molecules of a hot soup have high kinetic energy, whereas the molecules of a cold soup have a low kinetic energy. So to measure temperature, we have 3 different scales that we use to measure it. We are here in the United States, we're most familiar with the Fahrenheit scale, where 32 degrees Fahrenheit is the freezing point, 212 Fahrenheit is the boiling point. Scientifically, it is more convenient to use what we call the Celsius scale, where 0 is the freezing point of water and 100 is the boiling point of water. There is a third scale that's not very commonly known, but is also quite useful, and I'll explain why it's so useful in just a second. It's the Kelvin scale. The Kelvin scale works the same as the Celsius scale, only it's offset by 273 degrees. So 273 Kelvin is the freezing point of water, and then 100 degrees higher than that, 373 Kelvin is the boiling point of water. So if you were to track the temperature down to 0 Kelvin, that would be a temperature of minus 273 Celsius. Okay, so why is the Kelvin so important? Remember that temperature is a measure of the kinetic energy or the motion of an object. In the case of the atmosphere, motion of the molecules in the atmosphere. So what would happen then if the temperature dropped down to 0 Kelvin? Basically, your molecules will get slower and slower and slower until you reach 0 Kelvin, which is known as absolute zero, or the temperature at which all motion stops. Since you can't get any slower than stopped, there is no physical way to get a temperature lower than 0 Kelvin. So that's why the Kelvin system is so useful. There is no negative Kelvin temperature. 0 is the lowest you can go. That is absolute zero, temperature at which all motion stops. This figure in your book discusses some key temperatures that we've seen or will discuss in this course and how they compare on Fahrenheit, Celsius, and Kelvin. Now you can see here, boiling point of water, 212 Fahrenheit, 100 Celsius, 373 Kelvin, so on. And you can read all these yourself, including the hottest temperature ever recorded in the world, 134 Fahrenheit, and the coldest temperature ever recorded in the world, That's minus 129 Fahrenheit. I need to clarify, these are the highest and lowest surface temperatures ever recorded. We obviously have had temperatures higher and lower than those, but weather-wise, those are the highest and lowest ever recorded. All right, with energy done and defined, we can now talk about heat. Now, heat is often not understood very well. We often consider heat as some sort of object traveling from something that's hot to something that's cold. For instance, you put your hand out to a fire, there's heat, some sort of object moving from the fire to your hand. That is not true. Heat is simply the transfer of energy due to a difference in temperature. So what's happening with the fire in your hand is the fire is really hot, your hand is relatively cold compared to the fire, and so energy is being transferred from the fire to your hand. That is what we call heat. Now, when you have heat, or transfer of energy, this can cause one of two things to happen. You can either have a change in temperature or a change in the state of matter. And these two forms of heat are called latent heat, and then other forms that we'll talk about in the next video. But latent heat is a heat or transfer of energy which causes a change in the state of matter. In other words, it goes from solid to liquid to gas, or any combination. So for example, let's take something solid like ice. We melt it, turn it to water. And then we have our water, we evaporate it, turn it to water vapor, or a gas. Every time you do that, going from a solid to a liquid, or from a liquid to a gas, the water needs more energy, so it absorbs that energy from the environment. Okay? So when you're going from solid towards gas, energy is removed from the environment and absorbed into the water itself. If you go the other way, go from a gas to a liquid, or from a liquid to a solid, it no longer needs that extra energy, so it releases that energy back into the environment around it. And so there you have the entire cycle of solid, liquid, gas, and latent heat. Now, this is a very critical topic that will be brought up many, many times throughout the entire course. So be sure that you understand this principle of latent heat. So, what is a cloud? I'm going to just address that right now. What is a cloud? Well, in the air you have water vapor in the atmosphere. But as that water vapor condenses and turns into liquid, you get a cloud. A cloud is nothing but a bunch of liquid or solid ice particles. This cloud here is a liquid cloud. In Chapter 4, I'll explain the difference between a liquid and solid cloud. Anyway, that's beside the point. As the water vapor condenses to form the cloud, as we saw in the previous slide, going from a gas to a liquid, the water no longer needs that energy, so it releases the energy into the atmosphere around it. So the air around the cloud actually warms up slightly because of the extra energy released by the water. Now, in one thunderstorm, how much energy is released? Well, this is kind of a fun point. In one storm, there is more energy released by the condensation of water than the energy released in a small nuclear bomb. That's a lot of energy, and I think that goes without saying. But the difference is that a small nuclear bomb, all that energy is released all at once, whereas in a storm, it's all released gradually, but cumulatively, it's more energy than a nuclear bomb. Okay, that talks about heat in a state change. Heat resulting in a change in the state of matter. There are three other forms of heat that result in a change of temperature. These forms of heat are conduction, convection, and radiation. And due to the length, I will return in the second video to discuss these three forms of heat, and we'll discuss it then. So stay tuned for the second video. If you have any questions on anything we've discussed up to this point, please let me know, and I will get back to you as soon as I can.